Okay. Welcome, guys. So in the previous video, we already talked about definition of ring, and in the previous that we proved that or previous strange result that the finite integral domain must be a field. Oh, okay. So sorry. Finite commutative. Oh, sorry. In the integral domain, we already assume commutative, so finite integral domain is a field. Okay. So in this video, before we talking about homomorphism, I want to prove fact. Which I should prove it last time, but I forgot. Okay, so if a p is a prime, then let's say you define fp, right? So fp is a basically you just use a 0, 1 up to p minus 1, and the addition a plus b just the same as a plus b, right? But mod p, and times b if their products just defined to be ab and mod p. Yeah, so basically, for whatever it prime, whatever it exists p, and you just remove it. Okay, theorem, fp is a field. Okay, so maybe you guys already learned about the finite field, right? But how to prove it? So remember that we proved that the finite integral domain will imply a field, right? So in order to prove it, we only need to prove domain. Okay. Oh, sorry, it's an integral domain. Okay, so now it's trivial, right? Because if a b is 0 in mod p, because p is prime, right? By definition, p must divide a or p divides b, which means that a is 0 or b is 0. Okay, so the proof is done. Okay, so I also need to talk about a thing called the characteristic. So let me just quickly define. So characteristic, so if you have integral domain, so integral domain. So given an integral domain, and I say to be characteristic 0. Okay, so 0. So characteristic means that means what? Means that okay, so it means that if you take a non-zero element belongs to that integral domain A, and but you have some ma equals to 0, where m is an integer, then the only case is m is 0. Okay, so what it means that if you get a non-zero element A, and you try to compute a plus a, 2a, and you compute 3a and 4a up to keep it up to infinity, then all of it must be non-zero. Okay, must be non-zero. Okay, and so this is called characteristic 0. And on the other hand, so if I say the characteristic is it's k, so that means for any non-zero element in D, let's say this D, ka must be 0. Okay, so that means if you start from a plus a up to k times, then it must be 0. Okay, so this with this notation, then we can say that for the finite field P, then the characteristic is just P. Yeah, so I call CHARFP, right? It's just P, because in any field, if you times P, then it becomes 0. For any element, it times P becomes 0. So Px is 0 for any x belongs to domain. Okay. And then for the real numbers, rational numbers, complex number, your characteristic will be infinite. That will be 0. Right? Means that any there's non-zero element multiple times must still be non-zero. Okay. Yeah. So up to now we finish some discussion. Okay. So up to now we can talk about homomorphism. So up of the rings. Okay, so in previous step, we talked about group homomorphism, right? So let me just quickly remind G to G bar called group homomorphism if it satisfies this. So this is under a group structure. What about rings homomorphism, right? So rings homomorphism should be say if you have a ring R prime satisfies phi A plus B, phi A plus phi B. So obviously just follow this definition, right? So if it satisfies true property, it's called ring homomorphism. Okay. Okay, so there is a small stupid result. Phi of 0 is 0, right? By definition as a group. And your phi of A will be phi of negative A will be negative phi A. Okay, so this is a trivial exercise. Trivial. Okay. Okay, so the same story, we will define the kernel. So the kernel phi is defined to be all element belongs to a ring such that it maps to 0. Okay, so this is a definition, right? This 0 means the 0 element in the rings. Okay. Okay, so obviously that the kernel phi, right, will be a subgroup of R, right? Because we already proved that in the group theory, we already proved that this is a subgroup, right? But subgroup in addition. Okay. Okay. And then we also see there's a strange thing happen such that if A belongs to the kernel, if A belongs to kernel, let me just yeah, if A belongs to kernel, and then you take any R belongs to R, then you can check that RA belongs to kernel. So this has some strange property that you take any R and the product of A, then it become kernel. Right? The reason is that phi RA will be phi R, phi A. And then this is phi R is, I don't know phi R, right? But I know phi is 0. So I get 0 times anything, which is still 0. Okay. Okay. So this is the conceptual idea, which is called ideal of the ring. Okay, so we will talk in the next. I think we will talk in the future. Okay, so let's yeah, I think ring. Let's just talk about some interesting example. Suppose I talk about the real number at joint square root of 2. This means that we get sorry, let's call it z. So let's call it m plus n square root of 2, where m and n are both integers. Okay, so let's define we can define a ring homomorphism from z at the joint the square root of 2 to z at the joint the square root of 2 by just define phi of m plus n square root of 2 to be m minus n square root of 2. Okay, so you can check it. This is the ring homomorphism. Obviously, set 0 to 0, right? Yeah, and there are a lot of examples. So I think you can check online, right? Okay, so definition. So if you get two rings, there's a homomorphism. Then if it's also 1 and onto, then it becomes isomorphism. So this is the isomorphism as a rings. Okay. So two rings are said to be isomorphic if there's a ring isomorphism. Okay, and obviously that if the ring's isomorphism, then it must have the kernel phi 0. Okay, because this will be the injective. Okay. Okay. Okay, so now we can talk about ideals and the quotient ring. Okay, so up to now that so start from here, we will talk about some abstract idea in the ring theory, which the most important one is ideals. Okay. So people study a ring by studying their ideal. Okay. So let's talk about ideals. So you take a subset of ring. U is called by the way, U need to be non-empty. So it's called a two-side ideal. So it needs to be in all up to now we only talk so from here we only talk about the commutative ring with the identity. Okay, so we say that this is a two-side ideal. If so, definition is satisfied U is a subgroup of R. So U must is a subgroup if you only see the addition. And for any U belongs to U, R belongs to R. Ru will be U. Okay, so which tell you that if you take any element in R and any element in U, then product UR must be U. Okay. Also, since we only say two sides, so UR, RU and UR must be U. Okay. Okay, so up to now, we can define a quotient ring. Okay. So this is a little bit tricky if this is the first time you learn it. So quotient ring means that if you get ideals in R, then you can define R ma U. Okay, so I claim R ma U is a ring. So each element in R ma U, I write it as A plus U, where A is a ring. Okay, so easy to check that this is abelian group in addition, right? Because you can see that A plus U plus B plus U is A plus U. Because these U are sets, these U are ideal, and it's the addition is abelian group, right? So this U plus U is, so now U plus U is U as a set, right? As a set. Okay, and so the zero element is 0 plus U, and the inverse element is minus A plus U. Okay, so R modulo U in the addition is abelian group. Okay, and the multiplication is just A plus U, B plus U, just A, B plus U. Okay, because AU is just fall inside U and the BU fall inside U, right? So as a set that AU plus BU fall inside U, so also U squared is basically U. Okay, so or inside or basically a subset of U, right? So you get U, so you get 3 U's. So finally you get AB plus U. Okay, so this as a set is just means that multiplication also work. Okay. Yeah, so this R quotient U will become a quotient ring. Okay, so this is similar to what? Similar to if you get a so-called normal subgroup, then you can construct a quotient group. Okay, so quotient ring, quotient ideal, but the group quotient normal subgroup. So that you can view the ideal is the generalization of the normal subgroup. Okay. Okay, so yeah, so let me give you a final remark. So final remark that in a ring, in a group, if you get normal subgroup, then we can define a natural onto map, which is a G mapped onto to G quotient n. Right, so this is onto. So this is just the projection map to X to Xn, right? So from here that we can do the same thing, right? You can define a ring surjective on its quotient mod U by X mapped to X plus U. Okay, so this is the just the natural map. Okay, and what is the kernel? So the kernel psi is which map to 0, right? So kernel psi just X plus U become U, which is just U, right? So X U. Okay, yeah. Hope you guys understand. I think this is also trivial, right? Let me see how I'm saying. Yeah, okay, so let me just so there's a final theorem. So remember in the group theory, right, we spend a lot of time proving so-called correspondence theorem. Okay, so correspondence theorem tell you that okay, so let me just say. So in the group theory, we somehow like we say that if you get G bar, and then you get a homomorphism, and then you take the normal subgroup. You take a normal subgroup of it, and then the correspondence theorem says that any normal subgroup is pre-image. Its pre-image will be another normal subgroup of G. Okay, so which tell you that I mean, yeah, for normal it becomes normal, for the subgroup it becomes subgroup, right? And then it tell you that there is a correspondence between the left and the right. Okay. So for a ring, we still have the same. Let's say we get a homomorphism from R to R prime, and the kernel of phi is called U. So in this case, U will be ideal. So in this case, your kernel K is a normal subgroup. So from here that you can see the group theory and the ring theory has some similarity. Okay. Okay, so you say that you define this as onto, then you get your R prime is by the isomorphism theorem. You will say that your R prime is isomorphic to R quotient U. Okay. Okay, so this is the first. The moreover, the correspondence says that let's say that what. So let me just write in words. The sets of ideals. So sets of ideals in R prime. So you take R prime, right? Corresponding to one-to-one, corresponding one-to-one to the set of ideals in R, but greater than U. So I mean this, right? So basically, oh sorry, not U and I. Right, so any ideal between U and R will map to some ideal in R prime. So from these directions, we just map I to phi of I. And for another direction, just consider as pre-image. So if I prime here, just phi inverse I prime. Okay, so the set of ideals in R prime is one-to-one corresponding to ideals in the rings in the left-hand side in R, such that it covers contain U. Okay, so this is the one-to-one correspondence. So this is the same as the group theory correspondence. Okay, and that's it. And the next time we should talk about a maximum ideal. Just talking about some at least two famous ideal, maximum ideal and the prime ideals, and we will prove that if you get some ideal I in R, which is a maximum ideal if only if R quotient I is a field. So this is very elementary results. I think everyone in the undergraduate algebra should learn this. Okay, otherwise you should not pass. So if we get prime ideals belongs to R, then it become R quotient P will be a integral domain. Okay, and there are lots of ideal like primary ideal or fractional ideal. Yeah, but this we will not talk. We will not talk in this video. Okay, so next video, let's just talk about more ideals and quotient rings. Okay, see you guys next videos. Bye bye.